Good morning, guys. So, I hope you are all okay. The condition outside is not getting better. It's in a stack situation, the corona situation. I hope you are all staying at home, studying for your forthcoming exams. Okay, you have the slot exam also, so I think you are all studying. Today, we will be starting the final topic, the final module of our syllabus, that is called the design of Glantry Girder. That is the very important topic and a little bit different topic, a little bit tough topic. I will try to cover it in a easier way. We will have a interesting class for today. Okay. So today we will be starting our Glantry Girder. So let us open our notes, the Glantry Girder notes. Okay. So what is the Glantry Girder? First, we have to know about the overhead traveling cranes. Have you seen any overhead traveling cranes? In the picture, you can see I have given a overhead traveling crane. For your better understanding, let us open a EOT crane. What is the meaning of EOT crane? I will tell you. So I think you have seen that in roads or in a factory that for moving heavier members, heavier materials from one place to another, some cranes are used like EOT cranes, MOT cranes. EOT means electrically operated and MOT means manually operated. So electrically operated or manually operated cranes are used to lift heavy materials, heavy machineries from one place to another in the industries. And as I think in Kolkata, you have seen in the roads that in the work of metro that is being done here also there also the EOT crane is being used for placing pre-staged girders. Okay, I think you have seen that. So what I want to tell that the EOT crane moves in a member. The member is called the Glantry Girder. So you will understand how to design the member. Basically, we will see that. So let us first see what is the basic funda of a Glantry Girder. So Glantry Girder, okay. So now the manually operating traveling cranes or electrically operated traveling cranes. So two type of traveling cranes are there. So in this picture, you can see this is a diagram of our total EOT crane system. If you see the diagram, if you can see that these two are the Glantry girders. These two are the basic Glantry girders. This is the rail where the crane is supported, and in this rail there is there is a crane girder that is placed over the rail so that it can move in that direction as well as in that direction by the help of these wheels. Also, the pulley arrangement is connected with the crab. This is called the crab, where the pulley arrangement is connected, and it can also move in that direction. Okay, it can also move in that direction. So basically, this is the funda of the EOT, the crane system. So it can move here and also it can move here. So there are two type of movement in the normal EOT crane, as you can see. So let us come to this picture. You can see here that is the basic picture of a EOT crane. This is the rail where the wheels are moving like that. Wheels are moving here like that. Okay, and okay, let us take another. Okay, and this is the pulley to lift the member. This is the crab, okay, or the trolley frame it is called. It can also move in that direction and it can move in that direction. So there are two type of force. I will come later, horizontal and lateral and longitudinal force. It will be coming due to the movement. Okay, now why the design is somehow different? Because there is moving load in the member. Okay, so the position of the moving load, and due to the which position of the moving load the maximum bending moment is coming, we have to also know that, we have to also determine that. So this is somehow a bit different from all the members we have designed, because all the members that we have designed are basically with static load, that the load is a dead load or live load is a static load, but here the load is moving load, so we have to consider for that. Okay, now what are the general members that the Glantry girder is EOT crane is comprised of? The basic are the two consist of a bridge of two truss girder which moves in a longitudinal direction with the help of wheel connected to the crane girder. So this is the truss girder with the help with connected to the crosshead or end girder. This is the rail section on which, so in this picture you can also see that this is the rail section on which the girder is placed, the crane is placed, so it can move in that direction also, so this is the movement. Now all this, the rails are then placed in with over the Glantry girders. So these two are the basic of our diagram. The focus of our today's lecture is the Glantry girder. In the picture you can see the Glantry. Now coming to the Glantry girder, now here is another typical arrangement of a Glantry girder. So this is the Glantry girder. Okay, this is the Glantry girder. The rail is supported here, and this is the truss girder, and this is the crabs to hold the member. This is the column. Okay, this is the column. Why the column? This is the column. So where the Glantry girder is connected, and this is the diaphragm. What is the use of diaphragm? Because of a necessary clearance. Why the necessary clearance is required? Because of the lateral loads that are coming due to the movement of the crab, due to the movement of the crab. Force is coming due to the movement of the truss girder. A force is coming. Here you can see due to the movement of the crab, this movement, due to this movement, a force is coming to the wheel. That means to the girder, Glantry girder. Similarly, for this movement, another force is coming to that. This is called the lateral force. So due to these lateral forces, some clearance is adopted. To place the Glantry girder. This is called diaphragm of the Glantry girder because of the lateral loads they are placed. Now, in general, these are the some of the sections of the Glantry girder. You can see generally a Glantry girder consists a channel section like that. In general, we will see most of the Glantry girder that we will design are generally like that, a channel section and eye section. So it's a built up member, but built up member are of two rolled members are connected together to consist of built up member. Here is one type of connection where one channel, two eye section are connected together. Here is another, all the built up members. The angles are there, an eye section is there, another angles is there, the channel member is there. So these are the some of the arrangement that are used where the Glantry girder is there. Okay, so in general the Glantry girder is like that, a channel section placed over an eye section. Generally these are the Glantry girder. So let us now come to the design procedures of the Glantry girder, which is the most important part of our lecture. First, coming to the maximum wheel load, that to be first determination of the maximum wheel load, that is what is the maximum wheel load that will be coming to the girder. We will first see. So in this picture you can see a clear representation of which force comes to the girder is coming. This crab has a vertical load because there is a pulley suspending from it. So this is called a vertically downward. That is the first force. There are three type of force you can see. Number one is the reaction from crane girder acting vertically downwards. So this is the reaction. What are the reaction comprised of? Crab weight, the weight of the self weight of the crab, hook load, the weight of the hook that is connected, and weight of the crane frame. So the weight of the self weight of the crane frame. So this act as a vertically downward force. This is the first force that is acting. Second force is longitudinal thrust due to the starting or stopping of crane acting on the longitudinal direction. That means what is the crane? These are the crane girders. These are the crane girders. So this will also move. This will also move like that in that direction. So the starting or stopping of these crane girders. starting or stopping of these crane girders causes this movement, and due to that a longitudinal force is coming. This is called the longitudinal force or the thrust force. Remember that. Okay. Third one is the lateral thrust. This is due to the movement of the crab. This is the movement of the crab, because crab can also move. Hey, because to carry the members, so crab, due to the movement of the crab, lateral thrust due to the starting or stopping of the crab, acting horizontal normal to the Glantry girder. So these are the three forces that acts: vertical force, lateral force, and longitudinal force. Lateral force in terms of the lateral thrust, lateral force in terms of the lateral thrust, and longitudinal force in terms of the braking load. So that all works on the total wheel, that wheel, because all the loads are coming from that wheel to the Glantry girder. So the loads that are coming from that wheel is these two. Clear, I think. Okay, now coming to the how to calculate the load. That is our motto. So we know what are the forces that are coming to the member. Now we have to calculate what is the force coming to the wheel. That means what is the force in turn coming to the Glantry girder. Now the total load, lateral, longitudinal, vertical, acting is divided into the wheel, and thus the wheel load acting downward is actual load that comes to the Glantry girder. That I have told you, that is the wheel load. That all the summation of the combination of all the loads are coming to all the wheels. Then the wheel load is transferred to the Glantry girder. So with the wheel load. Now when the wheel load is there, it is this part is also important. Now when we are calculating the wheel load, now sometimes due to the crab is a moving member, also the crane is a moving member. Now when it is moving in a direction, sometimes due to certain reason suddenly it can stop, or suddenly it can start to move. So when a sudden load is applied, so the fatigue effect, the impact effect has also to be considered. The impact effect has also to be considered. What is the impact effect? Because the crab or the crane is moving, is a moving member. It can suddenly stop, or it can suddenly start. So due to that we are getting a impact load, that is a sudden applied load. I think you all both know that what is an impact load. That is a load that is suddenly applied. So the suddenly applied load is there. So due to this suddenly applied load, a impact load has to be considered. So how the impact load is determined? As per IS 875 1987 part 2 clause 6.3. Let us come to the clause. So this is the IS 875 part 2 that you can see. This is IS 875 part 2. Here clause number 6.3 says impact allowance for the crane girder. That means how much impact allowance we have to consider when we are determining the load for the crane girders. So vertical loads for the electrically overhead cranes, vertical load for hand operated cranes, horizontal load for transfer to the rails for electrical overhead cranes, and for all other electrical overhead cranes. So this is the value. So I have written all the values. In my notes also. So you can see this is all the values we have to consider. That means when we are determining the total load, we have to consider the impact allowance also. So for vertical load, depending on the type of the crane, EOT or MOT, that means the electrically operated or manually operated crane, we have to determine we have to assume extra amount of load due to this type of impact effect. For vertical as well as for the lateral and horizontal cases, we have to assume this amount of the load. So when we will consider the map, when we will determine the load in the map, when we are calculating the total load coming to the wheel, vertical as well as the horizontal, we have to consider this allowance also. We have to sum up this allowance plus the actual load. So please remember, when we are doing the math, we will take that effect also. Now coming to, therefore, first the actual, how the load, now coming to the main part, that how the load is calculated. As it is a moving load, when the wheel load, when the amount of the load will be maximum, that we have to determine. Therefore, first the actual load coming to the wheel or rail, that means if the roll is coming to that, I have told you that if the load is coming to the rail, it will be transferred to the as well similarly to the Glantry girder. So the load coming to the rail will be equals to the load coming to the Glantry girder. So therefore the actual load coming to the wheel is calculated. That means maximum reaction on each wheel is determined. That means if this is the rail and it is placed over a Glantry girder like that, so wheel load is there, so due to that a reaction force is coming. So how much reaction force is coming, that we have to determine. So let us see. So in this picture you can see maximum reaction force. Now the maximum reaction force coming to the Glantry girder will be determined only when. So now understand carefully. Now the crab is a moving member. The crab is a moving member. So we have to determine at which position of the crab when it will be the maximum effect of the load, when the if the crab where it will be placed. So as per the law, this is the position, this should be the position of the crab. Okay, this should be the position of the crab if we are determining the reaction in there, and it is, and if this is the position of the crab, the reaction is maximum on there. So determining the position, depending on the position of the crab, it can be here or there. Depending on the position of the crab, we have, this is the accurate position, this is the actual position when the maximum force is coming to the girder. That means when the crab is placed here, this reaction force coming to this girder will be maximum. So if we can design that girder, that girder will be similarly designed, because this is the maximum load coming to that girder, so that girder has to be designed. Similarly, if the load is coming to this girder, this wheel, so that girder has to be designed. Okay, and vice versa. So this is the actual position. What is now? It has to be placed at a certain distance. Okay, certain distance. It is called minimum approach. It is called minimum approach. That means how much minimum approach has to be also specified. So the minimum approach that will be given in your math. What is the minimum approach? So if the crab is placed in the crane girder at a minimum approach from the face of the Glantry girder, then the maximum load, maximum reaction force will be coming to the wheel. Now, so let us take that into a loading pattern. So this is the loading pattern. You can see in the loading pattern, due to the crab load, it acts as a concentrated force. Due to this, it has been said that point load due to the crab plus concentrated load on the crane, if the crab is placed here. Similarly, vice versa, if the crab is placed here, that load to be placed here. Okay, that load to be placed here. So only one position we have to consider where the load will be placed. So this is the point load due to the crab plus concentrated load on the crane. Now, and so why the UDL is here? Now listen very carefully. We are only considering the weight of the crab, but there is a weight of the crane girder itself also, because crane girder is a girder member. So the self weight of the crane girder has to be considered also. So the self weight of the crane girder will be acting as a UDL, uniformly distributed over the span between the Glantry girder, between those two Glantry girder. So this is the UDL is due to the self weight of the crane girder, and the point load is due to the weight of the crab. So I think it is both clear to you that why we are using both point load and the UDL, and why the point load is placed at a minimum approach, so as to get a maximum value of the reaction. So here from we have to determine the maximum reaction force R is determined. So what is the maximum reaction force coming to here? So if the load is placed here, the maximum reaction force you have to determine at, so reaction force at A support and B support you have to determine. We have to see which reaction is maximum. So we have to determine the reaction force from there. So that reaction force will be acting as the wheel load in the Glantry girder. So first the load is determined, the loading is determined by this formula. I think it is very much clear to you how the load is determined. Now coming to, so after the loading pattern, so the bending moment and shear force that coming to the Glantry girder has to be determined. Now step to determination of the maximum bending moment. It is very much important what will be the position of the maximum bending moment. Now consider this is the Glantry Girder. This is the column, one column, this is another column. Now the wheel load is coming from here to here. Consider the, generally in a crane two wheels are there. In a crane two wheels are there. Now this crane is a moving member, so moving load. So we do not know when the maximum bending moment will be there. When the maximum bending moment will be there, we do not know what will be the position of the crab as well as the crane girder. We do not know what will be the position of the crab and the crane girder. It may be here, it may be here, it may be here. So there is no actual position of the crane girder. So for that, but we need to find the bending moment, because if it is not a static load, we cannot find the bending moment. So for that, we have to assume some formula. We have to assume some formulation. What is said that the maximum moment due to the wheel load will be maximum when the CG of the wheel load and one of the wheel load, the CG of the wheel load and one of the wheel load are equidistant from the center of the Glantry Girder. If one crane is running over the Glantry Girder, if only one crane is running over the Glantry Girder, generally in one crane, in the picture you can also see that if there is one crane, two wheels are generally there. Two wheels are generally there in a normal single crane Glantry Girder. So when the single crane Glantry Girder we are assuming, so first we have to determine the bending moment. So the maximum bending moment under the wheel load will occur only when the CG of the wheel load and one of the wheel load, the CG of the wheel load and one of the wheel load are equidistant from the center of the Glantry Girder. So CG of the wheel load. So if understand it very much carefully. Okay, this is the basic part. After that it is very much easy, but this is the main basic part, the maximum bending moment calculation. So please understand that very carefully. This is one wheel load, this is another wheel load. These two are the wheel load, these two are wheels of the crane. Now the crane is moving like that, the crane is moving like that. So the crane will have the maximum bending moment when the CG of the wheel load, so this is the total wheel base, that means the distance between center to center distance between two wheels. So B, this is the CG of the wheel, this is the CG of the wheel and another wheel. What is the CG of the wheel load and one of the wheel load. So one wheel load and the CG. So the total reaction that is coming, from the wheel load to the Glantry Girder is due to the total reaction is R, that I have shown you here. So the total CG of the total load, that is the CG, that it will pass to the center, and the load of the one wheel. So these two are equidistant. So what is the distance between the CG of the wheel load and only one wheel? B by 2, because B is the total distance between the two wheels. So the CG of the wheel base, that distance from the one wheel is B by 2, because it is the center to center distance between the CG and the wheel. Now this distance should be equidistant from the center of the span. Now this center of the span of the Glantry Girder, consider this is the span of the Glantry Girder. Okay, now coming to the Glantry Girder. In the previous picture when we calculating the load, this is the span of the crane girder. Coming to the, now it is coming to the Glantry Girder. So this is the one column, this is another column, two columns are placed, the Glantry Girder is placed between them. So the span of the Glantry Girder, so it will be equidistant from the center line of the span. So this is the center of the span, midpoint of the span. So one wheel load is equidistant from B by 4 and the center CG is also equidistant from that. If only if these two, the span of the girder is placed at a position B by 4, the center of the span of the girder, Glantry Girder, is placed at a distance B by 4 from the one wheel and B by from the CG of the wheelbase. only when the maximum bending moment can be achievable, where B is the wheelbase and L is the span of the Glantry girder on the C-center distance between the columns, and R is the reaction force coming from the crane. So that is the total reaction force. Now here it is what I have told you. Here I have written that very much in a easier way, so you can see that the load can be calculated from there. Therefore, so actually the total reaction coming from the crane is equally distributed between the two wheels of the crane girder, because if this is the total load coming from the crane, so in each wheel that load will be divided in each wheel R by 2 and R by 2. We will need that when calculating of the bending moment. So R by 2, and therefore the maximum bending moment due to the applied load is determined, and then it is increased by a percentage as per the impact criteria. Now as we are considering only the vertical load, we haven't considered here, now very much careful here, we haven't considered any lateral loads here. We have only considered the vertical loads that coming from the crane and the self weight of the crane girder. We haven't considered any lateral load. So here when we are calculating the bending moment, also we have to increase the bending moment by certain of these two percentages, 25 or 10, depending on the type of the crane that we are using. So from here, so the percentage as per the impact criteria as step 1. Now the maximum bending moment that will be acting will be the bending moment due to the load plus bending moment due to the impact. So bending moment due to the load, that is the load, plus the bending moment due to the load that I have calculated from here, plus the bending moment due to the impact effect. So a certain percentage, 5 or 10% more of the total bending moment. So you have to sum all that and apply as the bending moment. Now note, we also have to consider, now when we are considering the, so this is the load reaction force. Now why the UDL is here, what is the role of the UDL? Now similarly, as we have considered when calculation of the load, we have considered the self weight of the crane girder. Here the self weight of the Glantry girder as well as the wheel is there. So if this is the Glantry girder, that we know, this is the Glantry girder, and over that our rail is placed. So for that member equally distributed load will be there. So this UDL is due to the self weight of the girder plus the rail that is placed there. So the bending moment has to be calculated with the considering both the reaction from the wheel load as well as the self weight of the girder plus the rail. We have to consider both of that. So here I have written that we also have to consider the self weight of the girder where the calculating the bending moment. Generally the self weight of the girder is not specified in the math. Generally we take the load of the girder between 1.5 to 2 kilonewton per meter, that we take the load of the self weight of the girder. So we have to consider the self weight of the girder plus the weight of the rail. We have to consider both of that. So that we need to be concerned about when we are calculating the bending moment. So after that the bending moment will be calculated depending on the bending moment diagram, the maximum bending moment, where it will be the maximum bending moment. Generally the maximum bending moment occurs under the load. Generally there are two type of reaction forces here. So depending on the reaction force, under the both reaction force you have to determine the bending moment, and from there the maximum bending moment we have to determine, where the maximum bending moment under this wheel load or that load, we have to determine the maximum bending moment for under these two loads. Okay, so after the bending moment, now we are coming back to the shear force. Similarly, as the case of the bending moment, for the shear force to a maximum. So here also when we are determining the bending moment, the shear force also we first cannot determine, because the load is a moving load. So the load, what will be the placement of the load, we do not know. So for the shear force to be maximum, what is the formulation? One of the wheel load is to be placed at support. That means one wheel load is placed at support. Another wheel, so the distance between the two wheel load is B, that is the wheel base. We know that. So only when this mechanism is considered, then only the maximum shear force will be there. So determining the maximum shear force here. Similarly, this is the self weight of the Glantry plus the rail that we know. from the previous step. So from here the shear force has to be determined. The shear force is also then multiplied with the 10% or 5% depending on the impact value. So the maximum shear force here is determined. So the bending moment and shear force we have determined. Now we are going for the design of the member. So step 4. Now the step 4. Now up to that we have considered only the vertical load. We haven't considered the lateral loads here. So now we have to consider the lateral load. Now the lateral forces on the girder is calculated and the bending moment due to this lateral force are determined. The total load, actual load coming to the wheel from the hook and crab. The total load, actual load coming to the wheel from hook and crab. This is the load. Okay. Now the total lateral force or surge force and the total longitudinal force or braking force. I think you all both know what is surge force and longitudinal force. This is the braking force, that is the longitudinal force, and this is the lateral force or the surge load. So for the lateral load and the surge load coming to the each crane is determined. Then factored load, first the lateral load and the surge load coming to the each crane is determined. Then the factored load is load factor, that is the value of the load factor that we will get from the IS code into the load calculated above. So we have to calculate the load above and then multiply it with the load factor. Now this lateral load, due to this lateral movement of the crab and the crane, the total load is coming onto the 4 wheels that we can see here. 2 wheels are here, 2 wheels are here. So if we are determining the total lateral load and longitudinal load, the total load that we have calculated, the factored load, it is coming on the wheels. So there are 4 wheels for a single crane system. So then we have to determine the load coming to one wheel. So what will be the load coming to one wheel? I think we can know that the load, lateral or longitudinal force on each wheel will be factored load by 4. It is very much important here. Okay, so factored load by 4, so the load coming to one wheel. Now so we know what is the load coming to the one wheel. So if we can know what is the load coming to the one wheel in the girder, we can determine the bending moment of shear force due to this lateral force. Now finally the bending moment and shear force due to the lateral and longitudinal force determined by proper proportioning. So here no formulation is used, proportioning is used. Proportioning means, if let us see maximum lateral bending moment, total bending moment on the girder by total wheel load. Now this bending moment that we have calculated is due to the vertical load. So the total bending moment coming here is due to the total load coming from the crane to the wheel. So here I have written that the total bending moment on the girder by the total wheel load on each wheel, that we know total wheel load, the reaction force on each wheel we have calculated. The total bending moment on the girder by total wheel load on the each wheel. This is the proportion. We have to multiply it with the factored load lateral force. By that we will get the maximum lateral bending moment. So this is called proportioning. So by the proportion of the vertical load with the vertical bending moment, we are determining the lateral bending moment. Similarly, the lateral shear force is also determined by the similar formula. So when we are determining the lateral and longitudinal force and bending moment and shear force due to the lateral and longitudinal force, we have to be clear about that. When we will need that? We will need that when we will calculation the local moment capacity. It is in the later steps, we will discuss that first, but this is the value. Okay, now coming to the step 5. I think so up to that the load and bending moment and shear force calculation is finally over. Now we are coming to the design. So we have to first determine the trial plastic section modulus. So we know the value of the moment. Similarly, as generally Glantry girder that I have told you, it is normally a laterally unsupported beam. So similarly, when in the design of a beam, we have seen that when we are starting the design, first a trial section modulus is determined. Here also the value will be same. The trial plastic section modulus is determined by that formula. ZPZ equals to 1.4 to 1.5, a value has to be taken in between that into mz by fy. Then a trial section comprised of I section and a channel section is provided. Now generally a I section is provided. Now for the now how to choose the I section and a channel section. So we have to know the depth of the section and the width of the flange. So for that, For economical depth and the width of the girder, following empirical formulas are used. What are the formulas? For economical depth of the girder, it should be more than L by 12, and economical width of the flange, it should be L by 40 to L by 30, where L is the span of the girder. So if we can determine the economical depth of the girder, means this D. So if we can determine the D, we can take one section of a I section. So the I section will be chosen based on that economic depth. Okay, it should be in between L by 12. So when we are determining the economic depth of the section, we can know what type of I section, what section can be chosen. So extra moment of extra section modulus that is left out will be covered with the help of this extra channel section. Okay, extra channel section will be used to cover the extra bending, section modulus that is required. So first the section modulus required determined, then the economic depth of the girder and economic width of the flange of the girder is determined by these two formulas. From there, a trial section is assumed. Then a I section and a channel section based on the calculated value is determined. Okay, so a section, trial section we can determine. Then step 6, we have to determine here all the sectional properties. Sectional properties means, what are the sectional properties we have to determine? We have to determine the sectional property like Ixx of the combine. Now, as we can see, it is now a built up member. We know the IZZ of the X member, we know the IZZ and IYY of the channel, but we do not know what will be the Ixx, IZZ and IYY of the total combined member. So first we have to determine these values like Ixx, IYY, ZPZ, ZPY, ZEZ, ZEY and the CG of the built up section. Total these things we have to determine first. Okay, so the sectional properties we have to determine. I think you all know how to determine a ZPZ, ZEZ, ZPY and ZEY of the total member, and IXS, IYY built up member, and Y section and a CG distance of a built up member. I think I have covered a lot of maths, a lot of conception to clear how to determine all this. So I am not determining any section. We will do that in a math. Okay, so this section has to be determined. Now coming to the section classification. Now there are two sections, one is a I section, another is a channel section. So section classification has to be done for the both of that. Now coming to the code, now we will need the use of code. Okay, so let us open a IS code. This is the IS 800. I think you both know what is IS 800. Now we do not think we do not need to use. Okay, let us stay. Okay, so coming to table number 2, let us come to table number 2 here. Okay, table number 2, I think it is here. So as it is a built up section but single in a, when we are considering it in a separate way, these two are the rolled members, rolled section. So for the rolled section, I think this is the formula for rolled section. Now these members are welded with each other. Generally a welded section is provided. So the channel and the I section are welded together. So this is a welded section. So for that, outstanding element of the compression flange, that means that case we have to satisfy that values, and internal element neutral axis depth wave for wave phase we have to determine that values. So B by TF and D by TW both has to be satisfied. So these are the values, one value, and this is the another value. So depending on the B by TF and D by TW ratio, the section is classified. That is, it is a plastic or semi-plastic or compact section. Then we see that what is the section classification. Generally always try to take the section in a plastic zone. Plastic section is generally provided. Okay, because if it is semi-compact or compact, the design procedure will be much more complex and the designer will need much more tedious work to design that. So generally a plastic section is always preferred. Okay, now this is step 7. So we have to check here the step 7, we have to check the section classification, okay, for each of the members, channel and I. Now come the step 8, coming to the moment capacity. check for moment capacity as per clause 8.2.1.2. Let us go to clause 8.2.1.2. I think 8.2.1.2. I think this is the code. Okay, 8.2 na. Oh, let us find here where it is. I think here. Okay, 8.2.1.2. okay, I have got it. I think 8.2.1.2. okay, now the moment capacity is determined by the following formula. MD is equal to beta B ZP Fy by gamma M0 factor design force, beta B ZP Fy by gamma M0. Now only when the factor design force exceeded shear force does not exceed 0.6 VD. So here this check I have shown it here also. This check has to be here also need to be done. Okay, so this formula we will use to determine the moment capacity of the total section. Beta B ZPZ Fy, so it should always be less than 1.2 ZE Fy by gamma M0 for simply supported. As it is a simply supported member, we have to check that also. So MdZ should be always greater than the maximum bending moment determined. So the maximum bending moment determined, it should be more than that. Now MDYF means the moment capacity of the flange member only. The moment capacity of the flange member only in y direction. So this is the formula to determine that beta B ZPYF Fy by gamma M0, it should be less than 1.2 ZYF by gamma Fy by gamma M0. Now coming to what is ZPYF. ZPYF is the plastic section modulus of the compression flange about YY axis. What is the compression flange? This is one flange, that is the total I channel section, and this is one flange of the I section. So the ZP we have to determine now only for this section, not the total section. So let us determine how to determine that. What is the formula? For your better understanding, I have written all that. BFC is the width of the channel flange, that we know. TWC, thickness of the wave. TWC is the thickness of the weight of the channel. BFI, width of the I section flange. Width of the I section flange. TFI, thickness of the I section flange, that we know. TFC is the thickness of the channel flange. Thickness of the channel flange. That means channel flange. Thickness of the channel flange, TFC, and BF, total width of the combined flange. So that the combined flange is the total width. That means the depth of the channel. BF is equal to the depth of the channel. Okay, now let us find out. This is the ZPYF. How to find out? So ZP means section, plastic section model. What is the formula for that? A by 2 Y1 plus Y2. If it is a normal rectangular section, normal rectangle section, if it is D by 4, if it is Y1 and a Y2, I think you all know that if it is D by 4, D by 4. So A by 2, A is B into D by 2. A by 2 means B into D by 2 plus Y1 plus Y2. Y1 means D by 4 plus D by 4. So here from here it is coming B square by 4. When the neutral axis passes to the center line of the member. Now when we are considering the Y section, you can see the neutral axis passes to the center of the channel flange, I section flange, and wave of the channel. But for that two members, we have to determine the ZPZ. So we will use this formula BD square by 4 here, BD square by 4 for the calculation of the ZPZ of this flange of the I section and the wave of the channel section. So flange of the I section B, that is the B means TFI into D means that thickness, D means Y section we are considering. So let us, okay, let us, so I have drawn this member like that here. Okay, so this is the YY section. Here you can see that for this wave member and this flange of the I section, the Y section passes through the CG of that section. So we do not need to determine the equal area axis here because we know what will be the equal area axis. So first we have to determine. So we are putting these values here also. So this is TFI and BFI square. So here this will be B, this will be D, and this will be B and this will be D for the wave, and this will be B and D for the flange. So B will be TF So I have written all that value. You can see all that value. Now for that wave portion, total length BF minus thickness of the channel flange. What is the thickness of the channel flange? That value TFI, TFC. So dividing all the values, we can now for that flange of the channel, we have to determine the section modulus. You can see for two flange, 2 into area into the CG distance. 2 into area into the CG distance. So this is the formulation for calculating the ZPYF. We will put the value there and determine the ZPYF. ZEYF, I think you know the total section modulus of the ZEY we have determined here. Okay. So we have calculated the MDYF. Now coming to the step number 9, combined local capacity check. So combined local capacity is checked by that formula MZ by MDZ plus MYF by MDYF. What is the value of the MZ? That is the maximum bending moment we have calculated in the earlier steps here. That is the maximum bending moment. Here we have determined the maximum bending moment here. Now coming to MDYF. What is the value of the MYF? Maximum bending moment due to the lateral load. That we have also calculated. This is the need of that maximum lateral bending moment we have calculated. So this is MYF. Okay, this is MYF. We will use this value as the MYF, maximum lateral bending moment here. So the value we have calculated here. Now coming to the step 10, check for the buckling resistance of the wave, because buckle will happen in the wave because the wave member of the I section is thin enough, so there will be buckling. It will act as a column section, so the buckling check has to be done. So as the general Glantry girders are laterally unsupported, then the bending strength also need to be determined from the clause 8.2.2. let us go to 8.2.2. so laterally unsupported beams, for that we have to calculate MDZ for that formula. So MDZ, beta B, ZPZ, FBD. So FBD is determined, I think you all know how the FBD is determined, by these formulas. So FBD, I have written all that here for your better understanding. XZLT, XILT you have to determine here. XILT you have to determine. LLT, lambda LT you have to determine. All the values we have to put here. ZPZ we know, we have calculated. So C1. Now here is one important portion. Why it is there is a C1. Here is no C1 here. Why it is a C1 is placed here. Now C1 depends upon the loading condition, which is taken from table number 12. Why it is C1? Let us understand. So here two wheel loads are there. So wheel loads are generally more than one. So for two wheel loads, two reaction forces, we have to calculate, we have to assume one factor. Let us go to table number 42 of IS 800. Table number 42, I think here it is table number 24, section 14, table number 24. Okay, here it is not, I think here. Wait 1 minute. So this is table number 42 of, okay, let me, okay, this is table number 42 of force constant C1, C2, C3, that depends on the loading. Okay, now depends on the loading. Now let us see what is the type of loading. So here in our design, this is our type. Two loads are acting here. Two loads are acting here. So for that, what will be the, depending on the value of K. K is the slenderness ratio. Generally the slenderness ratio here, it is taken as 1. Okay, it is taken as 1. Only we have to take the value. So what is the value of the C1 here? It is that. So if you want to see, this is the value of the 1.046. We have to take that. Okay, C1. I have written that also here. So 1.016. Now, so here you can see the formula is giving here. C1 is equal to that formula, C1 here. So we have to use the value of C1 from here. Now, we have to use the formula for C1 from here. So let us again open IS 800 2007. Okay, so this is the value of the 1.046 because of the two wheel loads are acting. Because of that we have to take the value. Because of that we have to take the value. Now coming to now here also we have to check the local moment capacity. For that we have to also determine the mdy. Mdy is determined from the that formula, zyt into fy by gamma m0. Mdy of the that portion, mdy of that portion. Okay, it is determined by that formula, section modulus of the top portion from the CG of the portion from the top portion, BD cube by 12 divided by D by 2, IZ of the channel plus half of the IZ of the I section. That is the value of the ZYT. We have to use the value here and determine the value of the MDY. MDY is equal to BD cube by 12. That is the total section modulus of the total section. What is that called? Moment of inertia through section divided by the Z by 2, because ZE, formula of ZE is that. Okay, formula of ZE is that. We have to use the formula here and determine the value. So IZ of the channel plus the half the IZ of the I section. We have to put the value here and determine the value of the MDY. Similarly, the combined local moment capacity has been checked here, MZ by MDZ, MZZ, that has been calculated by that formula. We have to put that formula here, and MDYF we have to formula MIF to put the formula here. Okay, so putting all the MYF, we have calculated the bending moment to the lateral force. We have also used that in the previous section. So the local capacity, it should be checked here. Okay, it should be less than 1 also. Now the check for the shear capacity. Shear capacity check is very much easy. Let us open IS code 800. IS 800. Okay, let's open IS 800 here. Okay, so check for shear capacity as per clause 8.4 and 8.4.1. so let us go to clause 8.4. I think it is here. Okay, 8.4 I think. Okay, so it is here. So from code 8.4, the shear capacity V should be greater than VD. That is the VD, Vn by gamma m0. Vn equals to AV FYW by root 3. The value is here. Now AV is the shear capacity, that the shear capacity of the wave. Shear is also only act on the wave portion. So always here the member is built up, but the two members that are connected are the rolled section. So hot rolled section we are using. So H into TW we are assuming for hot rolled section. So we will put the value of the AV here. FYW we know root 3. So it should be greater than the value of the VZ. Okay. Now what is the value of the H? H is the height of the I section only. So the channel we know, the channel is here, the I is here. Okay, so H means the height of the I section only, and TW is the thickness of the wave of the I section only, because the shear force is only act in the wave portion. So wave means the wave of the I section. Okay, so we have to calculate the shear capacity for the I section also. So this is the value for the shear capacity. Now as we are assuming that we are using that formula beta BZP gamma m0, that formula here, it is only can be used, this formula can only be used where it is this formula. This formula can only be used, if you can see here, this formula can only be used if it is a low shear case, 0.6 Vd. The design shear force does not exceed 0.6 Vd. So we have to also check that here also. Here we have to also check that the design shear capacity should be less than the shear force acting should be less than the 0.6 times the design shear capacity. We have to also check that, so that we have to prove that it is in a low shear case. Okay, up to that, this is all the basic works. Now coming to the some of the secondary checks. First one, the check for the wave buckling. What is the meaning of buckling? One second. So now coming to the coming to the check for the wave buckling. So when we are calculating the check for the wave buckling, the buckling resistance also we need to be checked for the wheel load under 8.7.4. Let us come to the clause number 8.7.4. I think it is here 8.7.4 where it is, right. That criteria we have checked in the previous day also in the plate girder. Okay, 8 point bearing stiffeners. So the bearing thing we have to check for that value B1 N2 TW FIW by gamma M0. Okay, B1 is equal to steep bearing length. Here the steep bearing length will be taken as the diameter of the crane wheels. Okay, remember that diameter of the crane wheels. It will be specified to you. Okay, we have to check the value. N2 will be taken as h by 2 into 2 into TW. H by 2, that is the height of the I section, by 2 plus 2 into the thickness of the wave of the I section. Now FCD to be calculated for the wave portion. Now for that the slenderness ratio of the wave has to be determined. It is 2.45 D1 by TW. D1 equals to that value. Okay, where R1 is the root radius of I section and TFI is the flange thickness of the I section. Where we will do the math, we will draw the picture and we can get a clear consumption from there. Okay, then coming to the check for the deflection. This is the check step number 14. Check for the deflection. The Glantry girder should also be checked for the deflection under the wheel load. The calculated deflection, the total deflection of the Glantry girder is determined as WL cube by that value, where L is equal to the length of the span, A is equal to L minus B by 2, where B is the wheel base that we know. The distance between two wheel is called the wheel base. Okay, this value is the wheel base. Okay, all right, this value is the wheel base. I is equal to the maximum gross moment of inertia of the whole built up member that we have calculated in the first cases, where when we have calculated the sectional properties here, we have calculated, we know the what is the value of the Ixx or the Izz we have determined here. So we will put the value here Izz, and generally Iz we have to check, and E is equal to elastic modulus of the steel that we know 2 into 10 to the power 5 Newton per millimeter square. So the deflection calculated should be less than, so the check has to be there. Where cranes are manually operated, the value will be taken from that. For UT crane up to 500 kilonewton load, the value will be that. Over 500 kilonewton load, the deflection will be that. And for other moving loads such as charging cranes, L by 600, where it is the length of the Glantry girder. So we have to check the deflection value from that. The calculated deflection value and the deflection value provided here, we have to check for that also. Now coming to the last for the design of the weld connection. Generally weld connection is preferred, so design of the weld connection has to be determined. Generally, to connect the channel section with the I section, weld connection is generally provided. Now the shear capacity of the weld, Q equals to V into A into Y bar by Iz. Okay, now what is the V? Maximum shear force of the girder that we have calculated, Vz that we have calculated. Iz is the Iz of the gross total area. A is the area of the channel section. Now that comes the question, why only the channel section area we are determining? Because the I section is not connected to the channel section. The I section is a heavier member. It is placed, the channel section is placed over I section, then the welding is done for that. So there is a chance that the channel section may come out from the weld, not the I section. So the area that will be acting, the shear capacity, the shear stress that will be acting, it will be on the channel member, because it is a thinner member and it is a lighter member than the I section. So the area of the channel section has to be determined. Okay, and as a channel to be connected for the with the I section, and y dash distance between the CG of the total section and the CG of the channel section. That means CYY and y. So this is the distance is y bar. So y dash, that is the total CG to CG distance of the built up member, and CYY, that is the value of the CG of the channel section that we know from the SP6, that is the steel handbook. So from that y dash is determined. From here the strength of the weld is determined. Strength of the weld is determined from that strength. So it should be, the strength of the weld should be greater than that value, Q value. So the strength of the weld has to be determined, and the strength of the weld should be greater than the value. After that the weld connection will be designed. So up to this is the design of the Glantry Girder. All the steps have been covered, all the checks have been covered. In the math, in the exam, depending on the depending on the marks of the question, you have to design that. You can skip the buckling check, you can skip the you can skip the buckling resistance check, you can keep the shear check for deflection depending on the marks that is coming. If it is a 15 marks question, you can do all the steps. You can also skip one or two lower important steps. Okay, so up to that, this is the total design of the Glantry Girder. I think the design is very much clear to you. It is somehow different because of the wheel load, but the total conception is clear. All the values are given. Next day we will do one math, and the next day we will sit for a introduction class. If there is a problem, please let me know, because it is a much more tough than the other modules, so we will get to know that one by one. So please go for that, study it very carefully, and then you will get the thing clear to your head. So please, all the steps to be remembered very carefully. Okay, do that well, and see you in the next class. Thank you. Stay home, stay safe. Thank you very much, student, for your time.